Hi, welcome back to another video tutorial about learning about neural networks. It's Sunday here, the weather is pretty fabulous, and today we will walk you through the code on building backward propagation into the value class that we defined earlier. So, getting back to our notebook, in the last video, we closed upon calculating the gradients for each of these input data. For example, let me refresh everything here. So this is the forward propagation with activation function as well. And we have calculated the gradients of them and have updated the gradients for each of the values or inputs or weights in the network. So while initializing all our gradients at 0, and now after manually calculating the gradients and updating the values, you can see that the gradients are calculated for every value inside it. Now, this is just one backpropagation where we calculated the gradients, and now in neural networks, we do this for thousands of iterations. So we need to come up with executable code where we no longer need to manually update the values of these gradients that are calculated. Rather, it should automatically take the data and calculate the gradients. So in order to do that, backpropagation starts with the last node. So the last node in our in this network is O, and since O is something that we initialized in our function, any initialization value or micrograd, as Andrew calls it, it has a value of 0 in its gradient. Hence, start with gradient 0. Now, so the gradient of O, that is dO by dO, O with respect to O, is basically 1. So the gradient of O is going to be 1. And let's update this network now. So we can see the gradient to be 1. So backpropagation starts by starting with the last node and coming back earlier. Now, in the last video, we have calculated the backpropagation formula for activation function tanh. If I can recall it, then Wikipedia hyperbolic functions. So this is a tanh equation, the non-linearity aspect that we add, just like addition and multiplication. And if we scroll further down, we can see that the derivative of tanh is 1 minus tanh square. So this is the backward propagation formula for tanh. Just like the forward propagation formula is exponential of e to the power of 2x minus 1 by e to the power of 2x plus 1. For the backward propagation, the derivative of tanh is 1 minus tanh square. So that's how we're gonna backpropagate and calculate the gradient. So let's start in this fashion, and let's calculate the tanh derivative. Now, so before even we go there, I would like to make sure of the self and the out data here. So tanh is basically called upon n, right? We're calling n dot tanh. Like tanh is activation function is called on n. So n here is going to be the self, right? Or yeah, n is going to be the self, and the output of n is saved in O. Out is returned and it's saved in O. So that means The n's output when passed through activation function is saved in O. So in order for us, so I'm just laying this basic terminology here. Now we need to calculate backward propagation of tan h. Just like we have forward propagation of tan h, we need to calculate backward propagation. So in order to do that, we need to write another function for backward propagation, right? So let's do self dot underscore backward, that is equals to lambda of no. So we are defining an empty function for every value class that we create. So if we look at O dot backward, that's a function and it returns nothing, it's empty. You can look at for anything. So x1 dot backward, that's also empty. So since x1 is a value, so we created a constant function known as backward, which is empty at the beginning. Now we need to define this backward. And the backward propagation gradient calculation formula for tan h is 1 minus x square. Sorry, 1 minus tan h square, right? Now, in here, tan h is this equation t. Tan h is e to the power of 2x minus 1 by e to the power of 2x plus 1, that is tan h. So the backward propagation formula is essentially 1 minus tan h square, right? Okay, so this is the backward propagation formula, but along with that, so the way we backpropagate is basically taking the activation function's gradient formula and multiplying it with the next layer's gradient value, right? So this is the equation for backpropagation of activation function, and how it should be multiplied with the gradient of the next layer. So here the gradient of next layer is O dot grad, right? Because O is the next layer, and the gradient for O is it has some value that we initialize. That we initialized as 1. So we multiply this with O dot grad. Now this will be saved. So this is, we took the gradient of O, we have the activation function's formula for backpropagation, we just multiplied it, and this output should go into n. This is the amount of gradient of change that n should have. So if you recall, n is defined in, tan h is defined in n. So n is basically self. So it's self dot grad is equals to the gradient equation for tan h multiplied with the gradient passing from the next layer as a backpropagation. Just like we take the inputs and multiply with weights to go to next layer, we take the gradient of next layer, use it to come to previous layer, use it on the previous layer to calculate the values or the gradients of the previous layer. Now, so this is a backward function that we created, and we need to call it. In order to call this, while initializing the variable itself or the value itself, we will call it. So we're going to do output dot underscore backward. This backward is basically the empty function that we define. So this empty space should actually always call our backward function. This backward is basically the tanet's internal backward function. So yeah, the names are pretty similar and can be confusing, but all we need to remember is this is the global variable that we defined, and that global variable holds a function. And all we're doing here is basically initiating the variable's function with the local function that we created inside tanh. Let me actually add some numbers so that it will be easier for me to refer. Yes, so now we've calculated the backward propagation of tanh. So we have O dot grad, and in order to, so if we look at this, we have O dot grad to be equals to 1. Now we need to initiate the backward propagation. So we will initiate this backward propagation on O dot backward okay, so O dot backward basically calls out this function, right? This function takes in self.grad. I mean, we update self.grad, and self.grad here is n, and because n is the one that we use to initialize the tanh, right? Hence, it updates the gradient of n. So we'll get n dot gradient, that is the updated value of it should actually be out because this is O basically that is named as out inside this function. So now if we do n dot grad, we'll be getting 0.5. Yep. So we are done back propagating for n. Now so tanh is one of the operation in the in our neural network. So we created backward propagation for tanh. Now we need to create backward propagation for additive as well as for multiplicative symbols. So let's go to their respective functions. So let's define backward propagation, backward function for additive model. So again, for the additive model, the inputs are self and other, right? So these are the values that we need to update. So we have updated n. So here the self is x1w1 x plus x2w2 and other is b, right? So n is basically an additive function. So x1w1 x2w2 is self and b is other inside this function that we created. So we need to calculate the gradient for plus, and we can clearly see, if you recall from our previous lectures, whenever there's an additive symbol, the gradient just passes along. That means since the gradient of n is 0.5, the gradient for b will be 0.5, and for x1w1 plus x2w2 will be 0.5. So we just need to pass them along. So in order to pass them along, we could define our backward function as since we have two data inputs for addition, we need to calculate gradient for 2. Hence self dot grad is basically 1 into the out dot grad. So out here is now n. So b x1w so b plus x1w1 x2w2 gives an output of n. Hence the derivative of x1w1 x2w2 and b is basically the output's gradient. So that's the reason why we do self.grad, which is x1w1 x2w2 is same as the output gradient. Now we need to update the same for the other parameter that we have in the input, that is self.grad, which is also equals to output.grad, and we need to save this function inside this initialization parameter. Hence, out.backward is equals to backward, right? And let's see. So we did n.grad. Now we need to do backward propagation of n. So we're going to simply call n.backward. This should update our gradients of x1, w1, x2, w2, and b. So let's look at the gradient of x1, w1, x2, w2. This is 0. Okay, so this is underscore backward. So now let's see the value. x1, w1, x2, w2 dot grad is basically 0.5, and b dot grad is also 0.5. If we update our graph, we can see that this grad value of n is now backpropagated to the other input. Perfect. So again, this can be applied to the same here. So since there is additive symbol here, the x1, w1, x2, w2's grad, which is 0.5, should go back to one layer where x2, w2 should be 0.5. The gradient of x2, w2 will be 0.5, and the gradient of x1, w1 will also be 0.5. So in order to do this backpropagation, we simply need to call x1, w1 and x2, w2 dot backward, right? Because this is our output and this is our input. Since we already have defined the backward function in additive function, we're just calling this will update our x1, w1's grad and x2, w2's grad, right? Perfect. So we're almost reaching to the beginning of our network, and if you could see the network that we created at the beginning is by multiplying the inputs, right? We took x1 inputs and weights. We took x1 multiplied with w1, and that yielded x1 w1. So in order to backpropagate, we need to find out the equation for multiplication transformation as well. So again, the multiplication has two inputs, self and other, so we need to update two of these values. Now recall from previous lecture, I'll go through this quickly, where the gradient of x1 is basically the data of w1 and the multiplied with the gradient of x1 w1. The same way, the gradient for w1 is the data of x1 multiplied with the gradient of x1 w1. So if we assume self, let's not even assume, let's see what self is. Self is x1 w1. No, wait. So self is x1 and other is w1. So let's update the self dot grad is basically equals to the other dot data, that is w1 minus 3 into grad of x1 w1. So the grad of x1 w1 is basically out dot grad. same way, when we do for other.grad, that's equals to self.data into out.grad. Now, this needs to be called in a function. I mean, this is just an independent function that's just hanging around. We just need to save this into the global variable. So we're gonna do this again. And in this way, in order to so in this way, we can calculate x1 w1 dot backward, which gives the gradient of x1 to be minus 1.49 and w1 to be 0.99. So if we update our graph, oops. Yeah, sorry. So we have x1, w1 with the respective gradients. And next, in the same way, we need to do it for the other input set, that is x2, w2. Let's just replace this. So x2.grad is going to be 0.5 and w2.grad is going to be 0. Ooh, that's interesting to see. Why is that 0? So our grad w2 is 0 because x2 is 0. We multiply x2 with respect to the gradient of x2 w2. So what does this essentially say? This means if our input does not have any value, then the weight associated with it will eventually become 0 after a couple of iterations, because the gradient calculated will be 0. So there's nowhere that we can change the weight W2 to make sure that we hit the optimal. That's because this node is essentially dead. This node doesn't have any value in it because our input is 0. That means they don't add any value to our overall neural network. And we can further conclude this when we have gradient to be 0. So this is the beauty of the mathematics derivatives just doing their thing. So so in this way we have added the backward component to every complication or every combination, every calculation that we perform. So to close this off, this is basically this. Yep. So this is basically one backward propagation while calling the next node, using the gradients of next layer or next layer. So again, this is a lot better than we trying to manually calculate and update. In the next video, I will go through the topology loop where we implement this as well in a good hierarchy of fashion, because even writing a bunch of these backward statements can be pretty exhaustive for every weight and bias, or for every node that we have in the neural network. So in the next video, we will automate this further. I hope you were able to follow my lecture. Please let me know if I need to take anything slow or need to elaborate on any specific aspect here. But all we were trying to do to summarize this is basically, instead of having to manually update these gradients, we have created an inbuilt functions for each of the calculations that we do, their equivalent backward propagation value, right? And this backward propagation basically updates the previous layer's gradients. So self.grad is basically previous layer's gradient using the current layer's gradient. Perfect. Awesome. Thank you for sticking by, and I hope you have a great time. And feel free to reach out to me for any queries. See you then. Peace out. Bye.